Linear programming plays an important role in the design and analysis of approximation algorithms, and we're going to take a look at several linear programming based techniques for approximation algorithms today by the example of the set cover problem. Ideally, before watching this video, you know about linear programs, integer linear programs, linear programming duality. If not, I have videos about that, but I will also have short reminders on these topics in this video, starting with linear programming as such and integer linear programming. So we have a linear objective function here written in vector notation. So you can also read this as c1 times x1 plus c2 times x2 and so on. So we have n variables x1 to xn, and we either want to minimize this objective function or maximize it, because the problem we're taking a look at today, the set cover problem, is a minimization problem. We will use minimize here as an example. And then we want to minimize subject to linear constraints. So those are written with a matrix A here, the vector of variables x, and this should be larger or equal b, again a vector. And we assume we have non-negative variables. So this is a linear program. Linear programs can be solved efficiently, both in theory as in practice. Now for today, we'll be focusing on the theory. And for that, it's important to know that we can solve those in polynomial time, meaning that if we can model a problem as a linear program, we immediately get a polynomial time algorithm. Unfortunately, many problems we cannot model as a linear program, but as an integer linear program. So the only difference here is that we're assuming that our variables are integers. Now this problem is NP hard, and therefore, if we can model a problem as an integer linear program, we don't directly get an efficient algorithm, but we want to approximate. And linear programming gives us several natural lower bounds for our problem, and lower bounds are crucial for the design of approximation algorithms. So which lower bounds do we get in linear programming, assuming we have a minimization problem for an integer linear program? So first of all, we can look at the LP relaxation of our integer linear program. What does that mean? It means that instead of enforcing that the variables are integer, we again get rid of that constraint and we get a linear program. So typically, in the settings that we're going to look at, our integer linear programs, the integer constraints will actually be of the type that we want our variables to be either 0 or 1. And then the relaxed linear program replaces this constraint by the constraint that the xi should simply be real numbers between 0 and 1. And then we have a linear program, and that we can solve efficiently. The other type of lower bound that we get from linear programming is by duality. So if I have a linear program, let's say the relaxed linear program for our integer linear program, and then I take the dual linear program, then if I initially had a minimization problem, then now I have a maximization problem, and any feasible solution to that gives me a lower bound for my original problem. I will say more about duality later when we actually use it, but those lower bounds give us various ways of designing or analyzing approximation algorithms using linear programming, and the ones we're going to take a look at today is LP rounding, the Primal-Dual Method, and dual fitting. Starting with LP rounding and by the example of set cover. So let's take a look at set cover, and we want to model the problem of set cover as an integer linear program. So set cover, we have a ground set U, so these are elements, and we have a family of subsets on this ground set. So these are now shown here as blue, and each of these subsets comes with a cost. And these are now these numbers 3, 1, and so on. And the set cover problem, or the weighted set cover problem, is now the problem of finding a collection of these subsets which together cover the whole ground set and this collection should have a cost that is as small as possible, and the cost is the sum of the costs of the sets that I collect or choose. So in my example, this would be 3 plus 1 plus 4 plus 5 half. If those are the sets that I choose for my set cover, they jointly cover the point set, and this in this example is also a minimal set cover. So how do we model this as an integer linear program? Our choices here is whether we want to pick a set or not. And therefore it's natural to have variables for the sets. So for every set, I have a variable which should be either 0 or 1. And 1 means I'm going to pick the set. And then the objective function is easy to write, because the objective function then is simply the sum. I want to have the sum of the sets that I select, and I get this simply as a sum of cost of a set times xs, because if xs is 1, I get the cost. If xs is 0, so I didn't choose the set, then this set contributes nothing to this sum. And now our constraints should make sure that we cover all of the elements of our ground set. So I will have a constraint for each of the elements. So those are called u. And they should say that this element should be in at least one set. And as a linear constraint, I can write this as the sum of the variables corresponding to the sets that contain that element should be at least 1. And I have such a constraint for each of the elements. Because if the sum is at least 1, because the xs are either 0 or 1, it means one of those xs is 1. It means I've selected it. So this is a set cover as an integer linear program. And what we're now going to do is we're going to look at the relaxed LP. So we replace this constraint of that xs should be 0 or 1 by that xs should be between 0 and 1. We can ignore the constraint that it should be at most 1, because there's no reason why we would want to pick xs larger, because it's always enough to make an xs 1, and then because it shows up in the objective function, I will never make it larger than 1. So the first technique will be based on using the relaxed LP and then taking the values of the variables and suitably rounding them, and therefore it's also called LP rounding. So let's have a look at this abstractly. So we have a problem that we can model as an integer linear program, and let's say this optimum has some optimum, obviously. Now the first step is that we're going to take the LP relaxation, solve it, so we get a solution for the relaxed problem. And let's say the optimum is here, and because I have fewer conditions or weaker conditions, the optimum will be better in the sense that it will be at most as large as the optimum for the original problem. And the idea of LP rounding is now to suitably take the variables that I get from the optimum for the relaxed problem. So I take an optimal solution for the relaxed problem and suitably round the variables to integers. And the difficulty here is to make sure that after rounding I still get a feasible solution. But if that is the case, so I have an algorithm which starts with the relaxed LP. By rounding, this is my algorithm, it simply rounds. I get an integer solution. So if I get a feasible solution, then the approximation factor I can calculate by taking the objective value that I get from my algorithm and divide it by the objective value for the optimal solution. Based on the rounding scheme, it will be quite easy to calculate this approximation factor. The difficulty will be in picking an appropriate approximation scheme such that I get a feasible solution and a good approximation factor. But before rounding, let's first convince ourselves that rounding is actually necessary. So here again is the relaxed LP. So how could the solution, the optimal solution to a relaxed LP look like, and in particular differ from the optimal solution for the ILP, so for the set cover problem. So let's take an example with 3 elements, and we have the following sets. Simply every pair we cover by a set that has cost 1. So how does the optimal set cover look like? The optimal set cover will have to pick 2 of the sets to cover all 3 points, and therefore will have a cost of 2. Now, if I don't require to take sets completely, but I can take fractional solutions, how can I cover this point set? So covering now means simply make sure that these constraints are fulfilled. So now I can do the following. I can now simply take each of the sets with an excess of 1/2, and in this way I cover all 3 elements, but my weight is actually, or my cost is actually only 3/2. So here the solution to the relaxed LP, or the optimal solution to the relaxed LP, is better than the optimal solution to the ILP, so we have to round. So let's first try something very trivial. Let's try to simply round anything that is non-zero up to 1. In this way, we definitely guarantee a valid solution, but the problem is it might be arbitrarily larger than the optimal solution to the set cover problem. And we can see that by the following examples. These are my elements, and I have many sets. So these are not yet many sets, but with these sets I can already cover it. So this is, if I have, let's say, n points, this is n-1 sets. But let's add more and more sets, and essentially I can cover this point set by taking each of these sets with a tiny fractional value, the more and more sets I'm adding. And this could be then, if I have to select all of those sets then into my set cover, could be arbitrarily much larger than the minimum set cover. So we need to decide how to round, and what we're going to use there is the frequency f. So what is frequency? The frequency of an element is the number of sets that contains that element, and the frequency f is the largest frequency among all of the elements. So the most number of times any of the elements is covered by sets. And we will now simply round xs up if it is at least 1 divided by f. Otherwise, I round it down to 0. Now we have to ask ourselves 2 questions. Why do we get a feasible solution? And then what is the approximation factor? The second one is easier, but let's first answer the first one. So why do we get a feasible solution? So what we need to make sure is that all of the constraints are fulfilled. So let's assume we have an element u. Now y is the sum of xs at least 1. So any element is in at most f sets. That's the definition of f. That means this sum here for any element contains at most f variables. But if the sum, and the relaxed LP guarantees that if the sum is at least 1, and I have at most f elements, then at least one of those elements has to be at least 1 divided by f. So this is by pigeonhole principle. Simply, if you have fewer than f elements and they are all smaller than 1 divided by f, then their sum cannot be 1. Thus, if I round everything up, which is at least 1 divided by f, then in the sum there's at least 1. I actually round it up, so the element is covered. What is the approximation factor that I get? So this is very easy. We have to see by how much do we increase the xs. So if something is smaller than 1 divided by f, I don't increase it, I actually decrease it, I'm fine anyway. Anything that is at least 1 divided by f, I scale up by at most a factor f. Because the smallest that I can get here is 1 divided by f, and I will need a factor of f to make it 1, but that's also the largest factor that I'm using. And then because of linearity, this means that I get an factor f approximation. So this is our first result here. LP rounding gives me a factor f approximation for the set cover problem. So you can actually get better or different bounds using LP rounding. More specifically, if we use randomized rounding. So what we do there is simply we take the XS and we take them as a probability of whether to round the element up or not. And then there's more work to be done, and we are not going to do this in a video, but I'm going to explain that in a future video. But with randomized rounding, we can actually get an O of log n approximation, or you could say an O of h of n, or approximation where h of n is the nth harmonic number. But now let's go to the next technique. And the two techniques that we now still want to discuss are both based on duality. So let's briefly remind us what duality is. So here we have a linear program, and every linear program has a dual linear program. So how does that look like? If I have a minimization problem here in my, what I now call primal linear program, then in the dual linear program, I have a maximization problem. And my matrix A here in the dual will be transposed. So I have A transposed here. And the C that is here in the objective function, and the B, which are my lower bounds in the primal LP, those switch roles. So I get B transposed here for the objective function in the dual, and C now as an upper bound in the constraints. And if I have x larger equal 0 here, then I get an upper bound here, and the larger equal here implies that I also have non-negative dual variables. Yeah, so this is a dual program to an LP in this form. And duality, if you have a minimization problem, the dual problem gives us a lower bound on the solutions of a linear program in the following sense, actually in two ways, but this is now the first one. So weak duality tells me that if I have a feasible solution to the primal problem, so let's call that x, and a feasible solution to the dual problem, y, then the objective value for the primal problem is larger or equal to the objective value for the dual problem. And again, this is in a setting where the primal problem is a minimization problem and the dual problem is a maximization problem. Because we're going to use this argument several times in this video, let's actually look at the proof, which is very simple. So we want to bound this objective value by the dual objective value from below. And here we can simply use the constraints. So here we have the Cj. So this could also be written as, or is actually simply C transposed X. Now I have in the dual constraints that A transposed Y is smaller or equal to C. So the C in the C transposed I can replace by A transposed Y. And because X is non-negative, I get, if I do this replacement, a larger equal here. So this is now simply plugging in this set of constraints. Now next, so here we have a double sum and we have yi and xj. We will rearrange the brackets, rearrange the sums. So now the sum over the constraints, the primal constraints or the dual variables, however you want to see it, is outside, and the sum over the variables is inside. So n, as you see here, n is a number of primal variables and therefore also the number of dual constraints, while m is a number of primal constraints and therefore the number of dual variables. Okay, so we rearrange these sums, again change simply the bracketing, and what we have now here is a times x, which we also have here, And therefore we can again replace it by b because we have that constraint, or we can upper bound it. And then because y is also non-negative, we get the bound that we wanted to get. So this is weak duality. And additionally to this, we can make a statement about the optimal solutions, and that is now strong duality. If I have optimal solutions, finite optima to the dual and the primal problem, so let's call these x star and y star, then the objective values are actually the same. So that is strong duality. We will need one more thing about a duality, and that is complementary slackness. So what does complementary slackness mean? If I have valid solutions to the primal and dual problem, so x and y, then these are optimal exactly if we have complementary slackness. And what does complementary slackness mean? It comes in two forms. We need to have primal complementary slackness, meaning that either the variable xj is 0 or the corresponding dual constraint, that is this one here, has no slack, meaning instead of so in the constraint we simply have smaller equal, but if xj is 0 and x is optimal, then we need to have equality here. And likewise, dual complementary slackness, if a dual variable has to be either 0, or if that is not the case, there shouldn't be slack in the corresponding primal constraint. So there I need to have equality. And this follows essentially by the same set, or using the inequalities that we just used, plus the strong duality. So we had these inequalities, and now let's have a look at these factors here. So we have x, c, j here, and the sum, so the a times a transpose y there. So now if we have primal complementary slackness, so if the xj is 0, then that summand doesn't contribute anything because it's 0. If xj is not 0, then the cj actually equals the corresponding term on the other side. So then it contributes, so that variable contributes the same to this sum and to that sum. Meaning, if I go through all the variables, either they don't contribute anything or they contribute the same. In both cases, they contribute the same. So then I actually have equality here. And the same argument goes here on the other side, using complementary slackness, the dual complementary slackness. So either yi is 0 or I have the same summand on both sides. So this is complementary slackness, and we're going to see that in a moment again, actually in a relaxed form. So the technique we're going to look at is the Primal-Dual Method or Primal-Dual Scheme. Again, we have a minimization problem. All of this will also work for maximization problems, obviously, but my explanations are all for minimization problems. And the idea is we start with a trivial solution. So typically we simply set all the y's and x's to 0. And this should result then in a feasible dual solution and, unfortunately, in an infeasible primal solution. And what we're now going to do is this solution that we have incrementally, we will make it more feasible. So we will make changes to our solution and make the primal solution more feasible in every step, always making sure that it stays integral. And this will also on the way increase the dual solution. This one does not need to be integral. And we do that iteratively until we have a feasible primal solution. So now I have here a feasible primal solution. We always keep the dual solution feasible. And after this process, the approximation factor that I get, I can estimate by looking at the ratio between the the primal feasible solution that I found and the dual feasible solution that I found. So this is my bound on my approximation factor. The advantage of this over LP rounding is that we don't need to do the LP relaxation, so we actually don't need to solve any linear programs. So while this is based on linear programming, we don't actually solve linear programs, but we can formulate this, as we're going to see in a moment, in a combinatorial algorithm. By avoiding linear programming, so explicitly solving a linear program, we typically get a faster algorithm and also get a more flexible approach. Since this is based on the dual, we first need to, if we want to again consider the set cover problem, take a look at how the dual problem looks like. So we have a minimization problem, so we're going to get a maximization problem in the dual. The constraints in the primal correspond to the elements. So in the dual, we will have variables corresponding to the elements. Now, if you take a look at the constraints here, so the B that we have is a vector with all ones, meaning that in the objective function in the dual, we will have as factors always a 1, so we simply get the sum of the YU. And our dual constraints, we will, on the right-hand side, get these costs, and on the left-hand side, we simply transpose A. So previously, we were looking at, for every element, the sets that it contains, so we had an adjacency matrix there, and this one we now transpose. So instead we get, for all the sets, all the elements that are contained in that set. So one intuition here, or how these LPs are also called if they have exactly this form. So the primal LP here is called a covering LP, and the dual LP a packing LP. Covering should be clear, we're doing set cover, so covering LP is intuitive. In the dual LP, why packing? Because we have these constraints CS, and we want to set the YU as large as possible so that for each of the sets, the number of elements that I'm packing, or the values that I assign to these elements, should add up to at most the cost of the set. So I'm trying to pack as much as possible into these sets to some regard. And these constraints are then also referred to as no overpacking constraint. So I'm not allowed to overpack. So one interpretation of this dual would be that I want to assign prices to the elements as to maximize the overall price, but I can only do so up to a certain limit, namely I cannot overprice any of the sets. To get an approximation algorithm, we are going to use a relaxed version of complementary slackness. So here you see complementary slackness. And let's first relax primal complementary slackness. So instead of asking for equality here, I now allow myself an error of a factor alpha. So instead of having this sum necessarily being Cj, it can be also smaller, but at most by a factor alpha. So this is relaxed primal complementary slackness. And for the dual problem, this equates to the following. So I have a factor beta, so I don't have to have equality here, but I allow myself that this sum of the aij xj can be up to a factor beta, still larger than bi. Again, it's always either xj is 0 or I have this, and either I is 0 or I have that relaxed complementary slackness. And what this gives me is, so I do not get equality now if I have a solution with relaxed complementary slackness, but I get an approximation. And the approximation factor, so this simply follows from the same argument as we already seen, just that we get an extra factor alpha and beta in the inequalities. So this will give me an alpha beta approximation. And typically actually either alpha or beta is 1. So in our setting we will actually have alpha as 1 and use beta only, but I'm introducing this more generally here. Now with this in mind, our idea is the following. As I said, we're going to start with a feasible dual solution and an infeasible primal solution. we're going to improve the feasibility of the primal solution. I'm going to see in this example of the set cover problem what I mean by that. And so simultaneously, this will also improve the objective value of the dual solution. We will now do so until we have achieved relaxed complementary slackness. Yeah, and while doing so, we always make sure that the primal solution is integer valued, and then we'll have a feasible solution to the primal problem with relaxed complementary slackness. And as we've just seen, this then guarantees me that I actually have an approximation. Let's do this by the example of set cover. So here we have again the primal and the dual problem and the relaxed complementary slackness that we're going to enforce. So for the primal complementary slackness, we actually will not relax it. So there I will make sure that we actually have equality, or the algorithm will make sure that we actually have equality. And the sets, so here we have a set. So if this is non-zero, I need to have equality here, and a set for which I do this, so a set where xs is non-zero, and therefore I am guaranteeing equality, we'll call these sets critical sets. What this then means is that we only are allowed to pick critical sets. So for the dual complementary slackness, we will actually do the following. So if yu is not 0, then, okay, I will allow myself a factor beta here, but I'm going to set beta to f. And what does that actually mean? So now I'm saying the sum of the xs that contain u, for any element u, should be at most f. Yeah, but this sum only contains at most f summons, or each of them is being at most 1. So this inequality holds trivially. Yeah, so essentially in the dual setting, we have something that we'll get for free, and we need to make sure to keep this primal complementary slackness. And we'll do so by the following algorithm. So initially we set all of the variables, the primal and the dual variables, to 0. Now, as long as there is an uncovered set, we do the following. We pick such an uncovered set, an arbitrary one, and now we're going to increase the corresponding dual variable until one of the sets becomes critical. So we're going to increase this up to the point where for at least one set, I have equality here. That set I then select as a critical set, and if it's several sets for which I get equality at the same time, all of those are now critical sets. I'm going to update the x accordingly, so I'm going to set the x to 1 for those sets, and then I'm going to mark all of the elements that are covered by these sets as being covered, so I don't have to consider them anymore. I don't have to set the y variable anymore. So let's take a look at an example. This is an example we're already using. So I pick an uncovered element. So let's say this one, any element would have done. I'm going to increase it until one of the sets becomes critical. This one is only in the set, and that set has a cost of 3. So I'm going to increase the yu to 3 here. At this point, this set becomes critical, and all of the elements in that set are now covered. So I've selected the set, those 3 elements are covered. I'm now going to pick another element. So let's say this one here. I increase the yu to 1 because at that point this set becomes critical. And then I'm going to select that set, mark the elements in that set as being covered, and continue. So for instance, now I might pick this element here. This element is in those 2 sets, this one here and that one here. Setting this to 4 makes this set critical. I pick the set, all of the elements are covered. Let's say I do this one next. So this is actually an interesting one because it's in 2 sets, but in this set I already have 4 and 1. So that set is already mostly covered up to 1. So by setting the yu here to 1, at that point this set is covered, the other one here not yet. And therefore I give this a 1, I select the set. I will need to, now let's continue with this one over here. Here I already have a 1, so this becomes 3/2. And finally I will have to set the yu for this element to 4. Now I have a set selected. I have the primal complementary slackness, and what we said about the relaxed complementary slackness, and knowing that we have the dual relaxed complementary slackness with a factor f, we now know that this algorithm, as I just described it, gives us a factor f approximation. We can ask ourselves, is the factor f tight for this algorithm? And we're going to see that by the following example. So let's say these are my elements. I have, let's say, f plus 1 elements, so my n is f plus 1. And I have, for one, all of these sets, so pairwise with a point in the middle, all with a cost of 1. And then I have one additional point, or one additional element down here. And I also have a set that contains all of the elements with a cost of 1 plus epsilon. Let's assume we pick the element in the middle first as an element that we want to cover. What happens? So I will increase the variable for that element to 1, because at that point, actually all of these sets become critical. I will set the variable for that element to 1. At this point, I'm then selecting all of those sets. All of those points are covered, except for the very last one here. The yu here at this point, this one has 1. All of the other ones have 0. Now, to cover the last element, because there's already a 1 here, this one will become an epsilon as yu, and at that point all points are covered. But at that point I also selected all of the sets, and all of those sets together have a cost of n plus epsilon, while there would have been a cover simply taking that one set of cost 1 plus epsilon. So I have essentially a factor n here, and if I set my n to f, this shows that the algorithm cannot achieve a factor better than f. Actually, we can observe that with this type of algorithm, so an algorithm that is based on duality, we cannot get a better approximation factor. And this is based on the so-called integrality gap. So the integrality gap is the ratio between the value of the optimal solution and the value of the primal solution, taking the supremum over all possible instances. And any algorithm that is based on LP relaxation or based on duality will have an approximation factor which is at least this large. So the integrality gap plays a large important role in the analysis of approximation algorithms. The last technique that we're going to use is dual fitting. And here we are not going to see a new algorithm, but we're going to use dual fitting to analyze an algorithm that we already know, namely the greedy algorithm for set cover. And if you don't know that yet, watch the corresponding video. So the dual fitting, abstractly speaking, does the following. Again, let's say we have a minimization problem and we have some combinatorial algorithm for this problem, which generates us a feasible primal solution. And with that feasible primal solution, I get an infeasible dual solution, which pays for the primal solution in the sense that its objective value is at least as large as the objective value of the primal solution. We're now going to take this infeasible dual solution and scale it down linearly to get a feasible dual solution. And if we can achieve that, then the approximation factor, or the bound on the approximation factor that I get, is exactly the scaling factor, because if you take a look at the optimal solution, so this is a upper bound for the optimal dual solution, which is an upper bound for the dual solution, the feasible dual solution that we had, which upper bounds the infeasible dual solution that we had divided by alpha. So this is actually here with equality. And this is an upper bound for the primal solution that we had, still divided by alpha. And if I multiply all of this with alpha, I see that I have an alpha approximation. Before jumping into the analysis, let's see the algorithm once more. So this is a greedy set cover algorithm. What do? We start with an empty set of covered elements and an empty set of sets in the set cover. And as long as not all of the elements are covered, we're going to pick the set that minimizes the relative cost, meaning I'm looking at the cost of the set divided by the elements in that set that haven't been covered yet. And the set that minimizes this, that is a set that I'm going to add to my set cover. At the same time, I'm going to assign prices, and this will make sense in a moment why we explicitly do so. Assign a price to each of the elements that I now newly cover, namely this relative cost of that set. That will be my price. Yeah, and then all of those elements are now covered. I add the set to my set cover and I continue until all elements are covered. So you might want to try this on this example. The result should be the following. So the green sets are the ones that I would select, and the numbers here are the prices that I pay for the elements. So for instance, the first set that I would be selecting would be the set with cost 1, because I get the elements at a price of 1/3, and that is the smallest price that I could get among all of the sets. Now, if we consider the sum of the prices of the elements, then it's easy to see that this completely pays for the sets. Meaning that the sum of the costs of the sets that I've selected is smaller or equal to the sum of the prices. And you can read this essentially off from the algorithm. So this is something that simply popped up in the analysis of the greedy set cover algorithm previously, and there might have been surprising. In the setting of linear programming, this makes a lot of sense, because these prices now correspond to dual variables. So for each of the elements, I have a dual variable, and I'm now going to set it simply to, so I'm going to set yu to the price of u. So here, once more, you have the linear program. This was the solution that we got, and the prices that we have here, those are the values that I'm going to take for the dual variable. This dual solution in general will not be feasible. So the problem is we might be overpacking the sets, if you think of this in terms of a packing LP, and that's very easy to see. Just take this set here. I should have packed only 3. I definitely packed more here. So we've overpacked our sets, but the trick now will be that we're going to scale, find an appropriate scaling factor such that we get a dual solution where we don't overpack. And what we're going to do is, instead of taking the yu as the prices, we're now going to take yu bar, which is price divided by the kth harmonic number, where k in our setting will be the size, the cardinality of the largest set in S. So in our example, k is 4 because I have a set with 4 elements, and hk is simply the kth harmonic number. And for the greedy algorithm, we can now use these dual variables as lower bound. So this we show in the following. So we want to show that the y bar are a feasible solution to the dual LP. That means we have to prove for that these constraints hold. So for every set, I need to show that I'm not overpacking that set. So let's pick a set. Let's say its size is L, because the largest set has size K, L is smaller equal K. Now let U1 to UL be the elements of that set in the order in which they were covered by the greedy algorithm. So if you have seen the proof for the approximation factor of the greedy algorithm not using LPs, you will notice that this is exactly the same proof, but now the dual fitting gives you more explanation to why we actually set all of this up as we're doing it. So now let's consider the iteration where UI was covered. At this point, if you think of our elements here, U1, U2, so this is U1, U2, and so on. Here we have UI, and this goes up to UL. At the moment where UI is covered, or just before that, all of these elements here are not yet covered. So from UI to UL, at least that many elements were not yet covered, and the number of these elements is L minus I plus 1. So we know at this point at least L minus I plus 1 elements weren't yet covered. We picked the set that contained UI, so the price should be at most the price that I would have paid if I would have picked S. Maybe I've picked S, but it should be at most the price that I would have paid if I picked S, because we have a greedy algorithm, and that price would have been the cost of S divided by the number of elements not yet covered, and this is at least, so here we have at least L minus 1 plus 1, so the price is at most this number. Now this means that the corresponding variable for that element UI is this number, the price, divided by HK. So that we have here. If we now take the sum of the dual variables of the elements in the set S, so we have that here, y bar UI, sum over all of those elements, then this is smaller equal, we simply plug this in. So we have this factor here for each of the elements, and then we have this number, and if we're going from 1 to L, so if you plug in L here, then I get L minus L plus 1, then I have 1, so 1 divided by 1. If I plug in 1, I get here L minus 1 plus 1, so L, so 1 divided by L. So overall, I get the sum of 1 divided by L plus 1 divided by L minus 1, and so on, down to 1 divided by 1. And this obviously simply is the Lth harmonic number. And since L is smaller equal K, this is bounded by the Kth harmonic number. So overall, I can bound this simply by CS. And with that, we know we have a feasible solution and a feasible dual solution. And therefore, we now know that we actually have a factor HK approximation. So let's have a look at this once more for the algorithm. So the objective value that I get from my algorithm is the cost of the sets that I actually selected, which I can bound by the sum of the prices. And now if we express this in terms of the scaled dual variables, we get the Kth harmonic number times the sum of the scaled variables. Yeah, because the sum of the scaled numbers variables is sum of prices divided by HK. And because this is a feasible dual solution, HK times the solution is a lower bound for HK times the optimal relaxed solution, which in turn is a lower bound for HK times the optimal solution to the set cover problem. This actually also proves that the integrality gap for this problem is at most HK, and it can be shown that it actually is that large, but we're not going to do that here. Another interesting observation is that from the dual solution, I actually get per instance estimation of the approximation factor, which might be much better than the HK. Because when I do my greedy algorithm, I get the sum of these prices. I can look at the sum of the prices and see how much do I need to scale them down to actually get a feasible dual solution. And that scaling factor, which might be much less than HK, is then already an upper bound on the approximation factor for that specific instance. So this might be much better than HK. So what have we seen today? We have seen that linear programs are very useful for the design and analysis of approximation factors. This is because linear programs give us natural lower bounds, namely through LP relaxation and through duality. And we've seen 3 techniques that make use of this: LP rounding, the Primal-Dual Method, and dual fitting. And the advantage of the Primal-Dual Method and the dual fitting is that we don't actually need to solve linear programs, but we get combinatorial algorithm, which often simply then also results in faster algorithms. In the next video, we are going to take a look at the concept of randomized rounding.